for this question, a tree diagram would best fit the scenario. So what I'm going to do is make a tree diagram based off of the numbers that they give me. So what I have first is whether or not it's a freshman or if it's a sophomore. So 70 freshmen of 100 students, which that reduces down to 7 out of 10. They also told us that 30 are sophomores, which they didn't need to give us that information because these would have to be complements of each other. This one's a little bit different then because it says of the freshmen, 50 are Indiana residents, and of the sophomores, 20 are Indiana residents. So we're not going from 10 to 9. What we're doing here is we're restricting our denominator to be the freshmen. So remember that there were 70 freshmen, and it says that 50 are Indiana residents, so this would be 50 out of 70, which reduces down to 5 out of 7. So complement rule, that means that not Indiana freshmen would be 2/7. So 7 out of 10 times 5 over 7 would then reduce to 1/2. 7 out of 10 times 2 over 7 would reduce to 1 over 5. And then same thing for sophomores. It says of the sophomores, 20 are Indiana residents. So remember there are 30 sophomores, so that's the denominator. 20 are from Indiana, so 20 out of 30 are 2/3. And then complement rule, this would have to be 1/3. And then I multiplied and got these values as well. And once again, I checked to make sure that these add up to 1, which they do. So now the tree diagram has everything I need. I just need to figure out what do I need from it. Find the probability that a freshman is selected given that the student selected is not an Indiana resident. So this is how we're going to restrict our denominator, not an Indiana resident. So here's a case where we do not have an Indiana resident. Here's another case where we do not have an Indiana resident. Remember, that's what that apostrophe means. That means Indiana not, so not Indiana. And so this is how we're restricting our denominator. So it's either this or this. So I would take 1/5 plus my 1/10. My numerator, it says find the probability that a freshman is selected. So remember, I need to work within the stars. I'm still restricting my problem. All right, so the rest of this is out. I couldn't go this route. I can't go this route because I know that it is not an Indiana resident. So the numerator, find the probability that it's a freshman. That would have to be this case right here. So that's going to be 1/5 out of whatever 1/5 plus 1/10 adds up to be. So just use a calculator for that to come up with that final answer of 2/3. This next one also is appropriate to solve with a tree diagram. It says people applying for a job, you either have qualified or not qualified. So that's what I have first. They're either going to be qualified or they're not going to be qualified candidates. And it gives us that 80% are qualified. So complement rule, that means that 0.2 are not qualified. Then the manager can either approve or not approve those applicants. So A for approved, A not for not approved. And it says they are approved. So of the people that are qualified, so that's this route, 90% of the time they are approved. So this is going to be 0.9, which means this one would have to be 0.1 because of the complement rule. People who are not qualified are approved 20% of the time, which means complement rule that they are approved 20% of the time, which means not approved 0.8 of the time. And multiply 0.8 times 0.9 to get 0.72, 0.8 times 0.1 to get the 0.08, and so on. Remember that all of these have to add up to be 1, which they do. Now it says find the probability that a person is not qualified. So not qualified is what we're trying to find, given that they were not approved. So first thing we're going to do is that given, restrict our denominators. They were not approved. So here's a case where they are not approved. Here's a case where they are not approved, which means that this is no longer a part of our scenario. This is no longer a part of our scenario. We are restricting this given that they were not approved. So our denominator is going to be 0.08 plus 0.16. The numerator says find the probability that they are not qualified. So here's not qualified, so it's going to be this one right here. So this is going to be 0.16 over whatever this sums to be. And again, use a calculator, and that's going to give us 2/3. This next one is also appropriate to use a tree diagram for. So if you want to pause the video, I will as well, and get that tree diagram made. So here's what you should have come up with a tree diagram with. So first thing is cancer or no cancer. All right, so they're either going to have cancer or they're not going to have cancer. And it said women in their 40s, that about 4% of women develop breast cancer. So breast cancer, that's going to be 0.04, and then complement rule 1 minus the 0.04. So this is describing women in their 40s. And this is data. I'm not exactly sure how old this data is, but at one point this data was based on true data. Anyway, then it talks about tests being positive and tests being negative. So someone that actually has cancer would receive a cancer test, and it's either going to come back positive or negative. And even if they don't have cancer, they don't know that. And it's either going to come back, their test will come back positive or negative. And so you have these true positives, you have the true negatives, but then you also have the false positives and the false negatives. So it says that the false positive rate is 24%. So what that means is a false positive means that their test says that they have cancer, but it's false because they really don't have cancer. So if your test comes back positive, that's what you're really hoping for. But that is 24%, so that's 0.24 complement rule. That means that they don't have cancer and they receive a negative test is 0.76. And then it says the false negative. Okay, so that's the one that you really don't want, because then that means that you really do have cancer, but your test says you don't. So that false negative is 0.28, which means the complement rule, this one would be 0.72. And then we can multiply and get what those and probabilities are. And once again, double check your work, add these up, make sure they equal to 1, and that's a good indicator that you have a good tree diagram. Then we just need to interpret, and it says if a 40-year-old woman has a positive mammogram, so this is what happens. We know this. So given that they have a positive mammogram, so positive mammograms, where are those? This one would be a positive mammogram, and this one. Okay, so once again, we are restricting. We're taking this out, because it says that their test came back positive. So that positive, that is going to restrict our denominator to whatever this sums to give us. And our numerator, then we need to figure out what we're going to include. And it says, what's the probability that she actually has breast cancer? So that's going to be this one. So that's going to be whatever 0.0288 divided by this sum is going to be. And using a calculator, that reduces down to 1/9.